So while the matrix equation AX equals B and the vector equation x1 a1 plus ... xp ap equals B. So while these are essentially the same except for notation, oh, this is the missing section. So maybe this will be good for everyone. They'll have an opportunity to print it or copy some stuff. So we're gonna go fast and easy today. Gives you some time before tomorrow. So while these are essentially the same thing, except for the notation of the AX equals B tells us something or helps us understand something new. So there's a case where the matrix equation represents an action on a vector that isn't directly connected with a linear combination of vectors. So here we're talking about linear transformations, and basically they're going to give us an action on a vector. So for example, if you look at these two below, you have matrix A times X, and if we multiplied these two things, we would have 4 minus 3 plus 1 plus 3. We could get 5 and 8. And so notice that we're saying that our input here is the vector x 1 1 1 1, and our output is the vector 5 8. So we are actually starting in 4 dimensions and we're ending in 2 dimensions. Or if we looked at the other, in the second example where we have AU equals maybe V, let's see, so you'd have 4 times 1 minus 12 minus 1 plus 9, so 4 minus 8, 9. So I think I've got 0 and 2 plus 0 minus 5 plus 3. I've got 0, 0 here. And so I got the 0 vector. So again, this first vector represents our input, and the 0, 0 in this case represents the output. So notice we're starting with this X right here, and we're multiplying by A, and we end up with the B that's over there. So it's like, we went under A, we started with X, and we went to B. Or we started with U, whoops, wrong color. Started with the U, and we went under A, and we ended with 0. Does this picture remind you of anything else you've seen in math? I kind of hope so. Think way easier than Laplace transforms. Think inputs and outputs. That's what I'm after.
Function?
Yeah, Gerald, yes, exactly. So this reminds us of a function. So we have our function, you could think about it like y equals f of x. That's kind of our old friend. Or maybe you could think about f. It takes in x's and spits out y's. And so in this particular section, 1.8, what we're learning about is we're learning about a special kind of function. Special function called a linear transformation. And the word linear should remind you of lines, like things you've done in the past. But this is a little bit, this is a little bit more general and different than what we've done in the past. But everything you've done in the past, well, almost everything fits. These will all be lines that actually go through the origin. That's the one thing that's weird about this. And a linear transformation is basically a type of function. And so we're going to be introducing this concept and walking through some of its ins and outs today. There won't be much in the way, or as much in the way of matrices today. Tomorrow we'll start, in 1.9, we'll play with the matrix side of this a little bit more. So a transformation T from Rn to Rm is a rule that assigns each vector x in Rn to a vector Tx in Rm. And when we say rule, that's like another math way of saying like a function. Functions, there's a little bit of a difference, but if you like the word function better, more familiar, feel free to use it. So notice that we are starting in Rn, and so we'd say the set Rn is called our domain. So it's the domain of T right here. Come on. And Rm would be called, if you have the domain in one case, then what would we call the other one?
Range.
You'd like to think that, but we don't. We call it the codomain. But I would have called it the range. So we call it the codomain. And so that's this set over here. Well, that's hard to read. This set there, this set there. Okay. And you'll see in the picture, you've got this codomain listed, and then notice that the word range also is showing up. And so we will talk about the range. So for x in Rn, the vector Tx in Rm is called the image. So the image of x. So you started with this x down here, and it gets sent to this Tx that's the image. It's like the, literally think about like the image, the thing that's on the screen, if you will. And the set of all images, Tx, is called the range. What color haven't I used here? Of T. And so in this case, the picture, the range is all the stuff on this plane, and it's made up of a whole bunch of different images. So the codomain is the whole space, the range is the part of the space that the function gets you to. Let me see if I can tie this into something that you've done in the past. So suppose we have just a nice friendly quadratic here. Okay, what's your domain? What's the domain here? It's all real numbers. Good. Should that be all this stuff? Okay. And so what's the codomain? So remember, codomain is like the world where all the outputs go to. It would be the vertical axis, and specifically it would be all of R again, because we're saying that all the outputs, and this would be positive and negative, like negative infinity to infinity in the vertical direction. So it's all the things that can come out. That's our codomain. How about our image? So our image says you take a specific value of x that's down here, and you get this y value, like this point on the y value is the image. So the y vals on the graph are part of the image. Okay. And then how about the range? You could imagine you have all these different y value showing up, not that last one, but your range would be from whatever this value is, y equals b, y greater than or equal to b, something like that.
So in the picture right there in 1.8, the cube would be the codomain, like the cube, like the light blue cube.
Correct. Yeah. Yeah, this whole thing would be the codomain. Yep. Good call. For to Gerald, most of the time we have R as our codomain. In the past, we've always had R as our codomain. But in this class, we're going to have multi-dimensional spaces as a codomain. And then did I answer your question, Andrew, in answering Sammy's? So we have a couple of notations here. And so another notation, or a couple notations are, you could say, we could say that T is a transformation that's going from X to T of X, or you could say T goes from X to Y, something along those lines. Or you could say, you could use like a matrix A. We're going to have this coming up. So you could say like A is going from X to Y, or you could say X is going to AX. What's in common in all these is we're talking about the stuff here on the left is the inputs. All this stuff is your inputs, and then you have your outputs on the other side. Those are all your outputs. And then in these notations where I have the colon, or the colon, what we're saying is that the T or the A, that's the name of the linear transformation. I see the question in the chat, and I'll get to that in a second. Just like we talked, so they're the name of it, just like we talked about F. They're sort of like F of X or G of X, something like that. Just like back in the old days, F and G were the names of the transformation. Now we're going to use T's and A's and B's and things like that. Ratana asked if I could go back and show where the codomain was on the picture. So the codomain would have been the whole thing, just like the domain was the whole thing, whereas the range is just the positive part. Let's look at an example. So we have A, which is some given matrix, and I'm going to give you a U and a B and a C, and I've got some transformation T, which is going from R2 to R3. So let me see if I can track. I don't remember my colors from before. So R2, this would be our domain. R2. And then R3, that's hard to read, would be your codomain. And the name of the transformation would be T, or maybe you could think about that as matrix X. All right. So we're going to define our function, our linear transformation T, as T of X equal to AX. And so you have a matrix A times X. And so this thing over here, well, here's your formula for the image. So in part A, we want to find the image of U. So find T of U. So this would be A, 1, -3, 3, 5. negative 1, 7 times u, which is 2, negative 1. And so to find the image, you're just going to multiply row times column. So 1 times 2 plus negative 3 times negative 1, which is 5. And then 3 times 2 minus 5 is 1, another 1. And then negative 2 minus 7 or minus 9. Okay. All this stuff is the image. Okay. So the image is, it's like the y values in our old world. So now in B, we want to we want to find an x in R2 whose image under T is B. So we need to solve A times x equals B. Something like that. So this is a matrix equation. What tool do we want to use to solve a matrix equation? Yeah, from Evan, we want to use an augmented matrix. So we have 1, negative 3, 3, 5, negative 1, 7, augmented with 3, 2, negative 5. And you can row reduce this. Anybody have it row reduced for me yet? I don't have. Oh, 3, 2, negative 5, 3, 2. I think it's not the identity matrix, Ahmed. I think you might have missed this minus sign right there. So I've got from Mahi 1, 0, 3 halves. And then 0, 1, negative 1.5, and 0, 0, 0. Something like that. Okay. So what are we saying? Like, what is this telling us? Yeah, so it's telling us that x equal to 3 halves, negative 1/2. Come on. Has image uh, 3, 2, negative 5. So we're going, our mapping is, it's going from here to there. under the linear transformation t of x equals ax. Whew. Okay. So C is really similar. So C is really, well, C sort of builds on this, and it says, could there be more than one answer? And from Ahmed and from Elijah, there are no free variables. So that's correct. So no, there's no free variables. Okay. Okay. And then in D, we wanted to determine if C is in the range of the transformation. I'm assuming you have your notes in front of you, so I'm just going to continue where I'm at. So is C, which was equal to 325, in the range? And we can go through a similar process to what we did before. Let's see if I'm learning this. Ooh, I'm learning. So here it is. The only difference is now you have a +5 here. Okay. And I think, I don't remember who it was. Somebody was working. Oh, Mahi was, no, Ahmed was working on this earlier. This row reduced to the identity matrix. Like that. But remember, this is an augmented matrix. So how do we interpret that result? From Felix, it's inconsistent. What does that tell you about the system? From Kevin, no solution. And then the actual question asked us, is C in the range? So what's the answer to the question? Yeah, so C is not in the range. Why the +5? Oh, the +5 was because up here, there was just a +5 in the original vector. Just the only change. So thank you, Twee. All right. So if A is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 0, then the transformation X going to AX projects points in R3 onto the X1, X2 plane. Because, and let's just kind of look through the math. Let's see what happens. So if I start with an X1, X2, X3, this is my starting spot, then this is going to go to, so here's my starting spot right here. We could ask, where's it going to go to? All right, well, it's going to go to 1, 0, 0, 0, 1, 0, 0, 0, 0 times X1, X2, X3, which is equal to what? When you do the multiplication, what do you get out? Yeah, from Evan, you get out X1, X2, and 0. So your output is A times X, which simplifies to this thing right here. Okay. Nice. And you could actually simplify this. So you could simplify this whole thing by noticing that that the third coordinate is always going to be 0, right? So since it's always going to be 0, like let's save ourselves a little bit of writing. And so we could write the whole thing as 2a equal to 1 0 0 0 1 0. Notice here I am 2 rows and 3 columns, whereas up above I was 3 rows and 3 columns. Okay. So here, what that's telling you is that if you started with you looked at A times X, this would be like 1 0 0 0 1 0 times X, which is X1, X2, X3. And the product here would be just what? Just thank you from Elijah and Mahi and Twee. So it'll just be an X1 and X2. And Prashant, I think you were starting in the process of typing there. So it's basically the same thing as before, except for we're going to save ourselves a little bit of writing instead of always having the 0 on the end. And so the point, or one of the points of this particular example, is that it shows you that notice how the dimensions changed. So down here, we had our A transformation was starting in R3 and it was going to R2. Example 3. So let A equal 1, 3, 0, 1. The transformation in this case from R2 to R2, defined by T of X equal to AX, is called a shear transformation. And there's a picture below that I think can be helpful. Hey, come back to me. So notice that you have a square that's being morphed into, I don't know, parallelogram of some sort. Okay. Does this have to do with? Gerald asked a question about dimensions. It does tie to span. It has more to do with trying to figure out the dimensions of the domain and the dimensions of the codomain. But we'll pick up on that thought later. So let's try to understand this image below. So maybe we could look at some examples. So let's think about this first point here. And so we could look at T and we could put in vector 2, 0 and ask ourselves what happens when we put in 2, 0 into this. So we would get out 1, 3, 0, 1 times 2, 0. And you're going to get out under that 2 times 0, or 1 times 2, plus 3 times 0, or 2, and 0 again. And so you're still going to be Come on. You're still going to be there. So green spot still under the transformation. Okay. What if we so this is going to go to looks like 6, something like that. So 6, 2, this would be this point right here. Okay. And then we could also look at the point, I don't know what color do I have left, orange. We could look at the orange point, T of 2, 2, which is 1, 3, 0, 1 times 2, 2. And this is going to be equal to 8, 2. And shockingly enough, if here's your orange point at the end, it's going to get mapped to that point there. It's a shear transformation like you'd use on Microsoft Paint or some drawing app. And it's also, I believe, the same shear as, for those of you that are in engineering, I think in statics and in statics you talk about like shear forces or things like that. I think it's the same type of like parallel type of shearings that are happening. So questions about this example? All right, well, we're almost there. Let's get to one more page, see if we can finish a section today. So this next thing is important. This is important. So a transformation or mapping of T is linear if it has two conditions, T of U plus V equals T of U plus TV, and T of CU equals C of, or C times TU for all scalars C and all U in the domain of T. Since the properties are true for all matrices, then every matrix transformation is a linear transformation. Though it's not always the other way around. Okay. Yeah, thank you for that, Croy, on shear stuff. So furthermore, if T is a linear transformation, then T of 0 equals 0. And T of CU plus DV equals CTU plus DTV for all vectors UV in the domain of T and all scalars C and D. Okay, so let's look at these really quickly. So T of U, or T of 0, would be the same as T of 0 scalar times any vector U. And by property number 2, we could take that scalar out. Here's that 0. And so this would be equal to 0 times T of U, which would be equal to 0 vector again. Here's my proof of the first part. And for the second part, T of CU plus DV would be T of CU plus T of DV. And then you can pull the C's and the D's out using property number 2. Something like that. So these right here are the mini proofs tied to this one. So here's this one and this one right here. Okay. So this second property here can actually be generalized to T of CV1, C1V1 plus dot, 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 CPVP equals C1 T of V1 plus dot, 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 CPTVP. And this is referred to as the superposition principle. In engineering and physics. It's basically why when you're in physics or engineering, you can split up all the horizontal components and the vertical components and treat them independently. Like that's what's going on here. It's a fancy way of doing something you've been doing for a while. All right. So how does this work? So in example 4, given a scalar r, define t going from r2 to r2 by t of x equal to rx. T is called a contraction when r is less than or, well, when r is between 0 and 1, and it's called a dilation when r is bigger than 1. Because it'd be saying something like t of 1, 2, example, equals like 3 times 1, 2. So here the r would be 3. So we're going to get out something bigger. We're going to get out 3, 6. It got bigger. So that would be an example of a dilation. From Elijah, doesn't this come up in differential equations as well? Yes. Yeah, this idea of superposition is a big deal in a lot of math. Yep. All right. So one last thing, and then we'll call it good. I'm sorry, I'm going to go just a couple minutes. But this is one important example. So I want to show that T is a linear transformation. So to show that T is a linear transformation, you're going to start with this statement here. You're going to start with T times Cu plus dV, and you're going to work your way through and try to show that the other side holds. So we're doing this for r equal to pi. So this will be r times Cu plus dV, or pi times Cu plus dV. And we can distribute that pi throughout. So we have pi Cu, pi Cu. I think that was in Lord of the Rings. Isn't that what Sauron said? And then pi dV. You can switch around where your C's and your pi's are. So we have C times pi u plus D times pi v. And notice that this is the same thing as C times T of u plus D times T of v. Therefore, T is a linear transformation. Make sure it's clear how this all connects. So to show this proof, what I'm doing is I'm using this statement up above, and I'm showing that one's equal to that one. Whew. Whole bunch of ground right here at the end.